Hello friends, welcome to the applied polymer rheology of polymer process engineering. In this particular segment, we will have a brief outlook about the flow of modified polymers and polymer with the supermolecular structure. Let us have a look about that the table of content what we are going to discuss. We will have a brief introduction, then we will discuss about the polymer filled with particulates. We will discuss about the liquid crystallinity. We will discuss about the polymer with the microphase separation in melts or solution. Apart from this, we will discuss about the covalent cross-linking of polymers. Now, in the pure or plain conditions, the polymers are rarely used in industry. So, because to improvise the properties, because to improvise the certain speciality aspects in those polymers, they are often mixed with different type of additives or different type of fillers. So, the list of additives that are used to change the properties of the polymer is extensive and diverse in nature. So, when we are having this kind of additives or fillers, then a lot of things need to be addressed. One thing is that what is their affinity between the additives and the polymeric chains? What is the synchronization of the chain? How they do impart with the other properties of the polymer? Apart from this, there are certain other ingredients like stabilizers, plasticizers, they are also being added in those polymers. So, that is why this particular approaches the discussion between the affinity of the stabilizer, plasticizer, additive, fillers and the polymer matrix is quite interesting, and we need to address all those things. Now, these stabilizers are sometimes process aids and sometimes lubricants, sometimes fillers, pigments to impart the flame retardancy, sometimes flame retardants, some impact modifiers. And apart from this, the fiber reinforcements, they are the best example of these kind of things. And ultimate aim of all these ingredients apart from the polymer matrix is to improvise the properties of the polymer. The different categories of nanoparticles, nanoneedles, they are somewhat more recent, and some of these have more significant rheological impact than others. Now, in addition to additives, fillers, stabilizers, the polymer frequently have morphology that results directly from the structure of the polymers. So, this makes them more and more complex in nature. The most prevalent illustration is the crystallinity. This is caused by the structural regularity. The occurrence of liquid crystal phases that last at temperature above the crystalline melting point is one that is less frequent. The rheological behavior of liquid crystal polymers, LCPs, is exceptionally unique. The polymers frequently have morphology which is the direct result of the polymer structure in addition to additives. The crystallinity, this is caused by the structural regularity. This is the most prevalent example. One that is less frequent is the existence of liquid crystal phases that last at temperatures higher than the crystalline melting point. A particularly unique type of rheological behavior is shown by the liquid crystal polymers or LCPs. So, let us talk about the polymers filled with the particulates, because all these things like additive fillers, they are the contributing part of this particular concept. The solid fillers, these can be added to the polymers to modify their properties at a cheap cost. So, in addition of coloring, the solid fillers are frequently added to polymers to raise their heat distortion temperature and a modulus, and sometimes the mechanical, thermal or chemical stability. As might be predicted, the fillers also make the resins melt viscosity higher. Is this a significant issue or does it have the little impact? Below we are going to over this particular query. The fillers occur in a variety of shapes and sizes and both they have an impact on rheology. However, they will all share the quality of being solid. This implies that the fluid around the particle must flow around them rather than through them. As a result, the viscosity rises. Now, the particles, they are closer together as the particle concentration rises. Now, influence of particle concentration on viscosity. The baseline influence of the widely spaced spherical particles on suspension viscosity is given analytically by Stokes-Einstein law, that is neta is equal to the m into 1 plus 5 over 2 phi p, where this neta m is the viscosity of the suspending fluid and phi p is the volume fraction of particles. Now, the Stokes-Einstein equation is important because it defines a lower limit for suspension viscosity. Although various tactics this can be discussed, there is nothing that can be done to lower the viscosity below this particular number. The particles' interaction become more important as the failure concentration rises. Now, if there are no attractive force acting on the particles, which must be hard spheres, then only hydrodynamic interaction occur. The Bachelor equation is frequently cited for these circumstances, and modest concentration, it is neta is equal to neta m into 1 plus 2.5 phi p plus 6.2 phi p square. Now, as it is mentioned, the coefficient of for this particular factor is only applicable to the spherical non-agglomerating particles. However, this equation introduces a quadratic term that implies hydrodynamic interaction between the particles. Empirical and semi-theoretical relationship covering much of the concentration range. Now, there are a couple of examples we have enlisted for the as a summary of a popular equation for suspension viscosity, like Stokes-Einstein equation. The neta is equal to neta m into 1 plus 2.5 phi p. Now, Mooney, this is the neta is equal to neta m exponential 2.5 phi p into 1 plus phi p over phi max, or neta is equal to neta m exponential k e phi p into 1 minus phi p over phi max. Similarly, Maron-Pierce equation, Rosique equation, and Frankel-Arquiv equation, all these equations are enlisted for the advanced study or references. Similarly, the Krieger-Doherty equation and the Hartwig equation. So, all these equations we have enlisted as a reference, and as per the case this can be utilized. Now, these applicable to the Newtonian response of the suspension of non-interacting hard spheres. Here the neta m is the matrix viscosity, whereas phi p is the particle volume fraction in every equation, and phi maximum is the maximum packing fraction, and Ke is the Einstein coefficient. For more general equation, this can be replaced the constants 2.5 with Ke, a parameter, and these are valid only for high concentration. Now, there are numerous empirical or semi-theoretical connections that cover most of the concentration range. Now, this table has an example. You should take note of the fact that a number of these equations diverge at an upper limit of phi maximum is less than 1 for the volume fraction of a solid particle in the suspension. Although it can be inferred from the particle concentration in the sediment at the bottom of a well settled dispersion, in practice this bound can be a little tricky. For spheres that are uniform in size and randomly packed, the answer is phi maximum is almost equal to 0.64. By fitting the viscosity data at intermediate concentration, both Ke and phi max are often extracted from these equations application. The equation can be applied in this way to describe the viscosity of suspensions of slightly asymmetrical particles. The issue of how to pack more particles into polymer is crucial, or a particular concentration viscosity, or to decrease it. Changing the particle size distribution so that small particles are distributed into voids is the simplest method left behind by the big ones. Let us talk about the non-rheological properties of the polymer-based suspension. The particle suspension's non-linear rheological characteristics can be extremely complex. Thus, they won't be discussed in any detail. Now, it should be very clear in mind that the reaction is influenced by all of the complex structural factors like size distribution, stabilization, and concentration. The shear thickening, time dependency, and the dilatancy are among those phenomena. Now, in this particular figure, the HDPE melt filled with various amounts of titanium dioxide solids the data are gathered. Now, using a cone and a plate rheometer open using capillary, the upturn in the viscosity at lower rate is taken as an indicator of the presence of the yield stress. Now, one of the basic suspension imaginable with a spherical glass beads suspended in a polymer melt as per this particular figure. If one can recall that the power law exponent ranges from 1 for a Newtonian fluid to 0 for a material that is extremely thin under shear. The data in this particular figure thus imply that adding particles make the suspension more pseudoplastic. The presence of higher than average shear rate between the particles and the particle propensity to the organize into the layer under the steady shearing, they are the two potential explanation for this particular aspect. But one need to exercise very cautiously. The development of the yield at a relatively low volume fraction or filler is a frequent finding in particle filled polymer solution and melts. As per this figure, where the sample is melt of high density polyethylene containing titanium dioxide. Let us talk about the particle anisotropy. Now, for a given volume fraction of solid particle that form cluster that resemble strings would produce suspension with a high viscosity. The rubber industry has been aware about this particular occurrence for a long time because of their high structure carbon black products contain string of carbon nanoparticles. Silica nanoparticle have also been observed to string. Why is it so? First of all, in the absence of a strong long range repulsive force, the high specific values of interfacial energy of a small particle suspension particularly guarantee that the particle will aggregate. The reason a string forms instead of a clump is related to the end particle's extremely potent localized axially directed attraction to unattached particles. Now let us take the example like polycaprolactam melt filled with the various amount of hydroxyapatite nanoneedles. Now these tests were conducted at 120 degrees Celsius at melting point of PCl is about 60 degrees Celsius, and the line is to fit the psi of is equal to 0.1 data with the Papan Institute model. Now the PE is the upper scale stand for the Packlet number, which is the ratio of the shear rate and Brownian rotational rate of the needles. A large value such as on this particular graph indicates that Brownian motion is too slow to affect the orientation of nanoneedles. Now, if we talk about the stabilizing particles in the polymer suspension, the reduction of interfacial energy by attaching a cationic surfactant to a negatively charged particle surface in place of original inorganic cations. The particle acquires a more hydrocarbon like character due to the alkyl group on the quaternary ammonium cation that have displaced the sodium cation from the particle's surface. Now, agglomeration, this can be avoided, not really, at least not without also changing the matrix of the property. And that is why the particle surface is significant as in the interfacial energies to start. The typical method to add the surfactant which results in creation of an inverse emulsion of a polar particle in a continuous organic matrix, the particle. The surfactant can be useful but they must have a low solubility in organic matrix and hydrophilic head with the low charge. Otherwise, it is likely that they will interact electrostatically negatively. In the matrix, non-ionic surfactant are probably excessively soluble. A quaternary ammonium cation surfactant replace the cation on a negatively charged particle surface as a suitable compromise. Two of the four alkyl groups, they are typically shorter and two are bulkier. Grafting alkyl substitute silanes onto the neutral particle surface is replacement of for ion substitution. Now this works well with some particles like glass or silica, but not so well with others. A water resistant interface is a significant advantage of silane treatment, and if not, the composite's mechanical quantities or qualities in the damp application may dramatically decrease, and that is undesirable. This is the schematic diagram showing the crowding of polymer chain on particle surface, leading to protection against particle agglomeration. So, if we attach a polymer group to the surface particles, this can also be stabilized entropically. In this way, even gold nanoparticles can be stabilized. The objective is to have enough chains on the surface to diminish the degree of freedom of the interacting chain as two particles approach, causing the particle to move away. Now, if the chains are lengthened as the particle they are separated, this works well. Now this suggests that the chains on the surface are miscible with the matrix, which may be a challenging criteria to satisfy. Otherwise the particles will bunch together and the suspension would behave as an incompatible polymer blend. Let us talk about the electrostatic stabilization. The stabilization of a tiny particles in water or other extremely polar fluids by attraction of a similar charges on their surfaces is known as electrostatic stabilization. It can be represented by this particular figure. Now the particles chemical makeup may already contain a charged surface, or it may be added to be strengthened by covering the particle surface with a polyelectrolyte. The favorite neutralized polyacrylic, this may cause a surface to become extremely anionic if they adhere to the particle surface and they are subjected to high pH solution. Of course, there are an equal number of cations to on counteract to the negative charges on the carboxylate group, but in water these cation will have a floating around and interacting with the water's anion. A net negative particle charge is the outcome in the essence of the particle is a big and highly charged anion. Let us talk about the liquid crystallinity and rheology. Nanoparticles keep their stiffness as they get smaller and start to behave more like molecules than like particles. On a mole basis, particle-particle interactions are analogous to the entropic terms as particle diffusivity rises. Such particles in polymers could be anticipated to behave like solution with potential for phases with various concentration and shapes. The solution of rigid rod or rigid plate like molecules which create liquid crystal phases are most similar to suspension of rigid nanoparticles. Simply put, a liquid crystal is a liquid in which the molecules are arranged in a stable manner due mostly to their anisotropy. The liquid crystal phase might consist of one element or combination of elements. The first type is known as thermotropic liquid crystal, whereas the second is lithotropic. It is interesting that not many systems exhibit both behaviors. Additionally, the, the rod shaped polymers molecule, this can generate liquid crystal solution with extremely intricate rheological characteristics. Despite its hard helical shape, polybenzyl glutamate is one commonly studied system when it is dissolved in one of many appropriate solvent. The larger benzyl group contributes to good solubility in a variety of typical polymer solvents. But Kevlar, an aromatic polyamide derived from the terephthalic acid, really the acid chloride and 1,4 phenylene diamine may be the most commonly used lytropic liquid crystal (LCP), and to break up the normal intermolecular hydrogen bond between adjacent chain, the Kevlar needs a strongly protic solvent such as sulfuric acid. Now, polymers with the microphase separation in melts or solution. The microphase separation is typically thought to be connected to polymer structures that differ in constitution or configuration. The presence of microphase separation and alteration in the rheology is flexible polyurethanes with rigid aromatic segment, block copolymer, and even random copolymer is not at all surprising. The rheological behavior of polymer solution with homogeneous structure, random arrangements and no sign of crystallinity is truly remarkable. Now, this particular figure represents the schematic of the cyclic dimer by hydrogen bonding of two carboxylic group covalently bonded to polymer chains. Some of the events caused by the physical relationship between the polymer chains, we are going to discuss that particular thing. One is the hydrogen bonding. The typical structure seen in the polymer, the strength of hydrogen bond is typically in the range of 30 kilojoule per mole. Now, usually RT is approximately 4 kilojoule per mole at 200 degrees Celsius. As a result, we can see the hydrogen bond can easily survive in the melt of many polymer while being weaker than a covalent bond. Now, the cross-linking, physical cross-linking, there are several rheological phenomena that involve even lesser secondary forces. The gelation of polymer solution containing low polarity linear polymer is most striking. Now, this particular figure represents the schematic representation of a sticker decorated polymer chain showing some stuck but many free. The chain on the left, this one, has two stickers and thus can be mechanically active in a gel. The system containing polystyrene and a carbon disulfide is a classical example. Because it is a linear molecule like carbon dioxide, the carbon disulfide lacks a dipole moment, while the phenyl group and the modest segmental dipole moment of the polystyrene may interact. It seems unlikely that these weak interactions will result in a sudden shift in rheology. Let's talk about the covalent cross-linking of polymer. If weak interactions in polymer solution, there are strong covalent bonds, one may anticipate that all of the difficulties associated with weak contacts would be eliminated. Now, this is accurate up to a point, but there are other complications. Starting from fluid, there are numerous approaches to create a cross-linked network. So, if the fluid is a polymer melt or a solution, crosslinks must be created in some way, either through radiation or a chemical curing or with the help of a reaction of already existing group over the chain. Now, there are numerous examples when a polymer begins as an oligomer or a monomer, it is polymerized and simultaneously cross-linked to create a gel. Polyurethane, silicons, epoxies, thermoset polymers, bismilamides, polyamides, they are the couple of examples who can represent like this. So, dear friends, in this particular segment, we discussed about the rheological behavior, we discussed about various kind of the bonding among the polymeric system, and especially when we talk about the particulates in the polymer, because no one can overlook the importance of this particular affinity. So, we discussed all those things and what is the impact of this one, how this can be covalently bonded or hydrogen bonded play a role. All these things we have discussed in this particular segment. And for your convenience, We have enlisted these 7 references which you can utilize if you need further studies. Thank you very much.